Hi, everybody. I'm happy to see you again. For those that for check that it's not the first time that we see each other. Rich, I don't remember if you were there on at another live session, but happy to see you. We are going to jump into that session. This is a session of 1 hour and a half. And it's a bit. We are going to do it a little bit casual, if we can say, because we are not really going to write code. We are not really going to go through the bolts, but we are going to go through some code, add some print statement to try to understand what's going on with the LnMessage library, commando. And the noise protocol and all of that stuff. So one disclaimer, as the Bolt 8 and how the nodes can connect together uses a lot of cryptography. I prefer to say beforehand, so I'm not a cryptographer, so if you know more or I say some of the thing the wrong way, please correct me. But I think that we can still go through that session. Let's go. So here we go, and maybe the best way. So I have almost no notes because I want to go through the code as if we were discovering how this is working. So please, if at any moment you want me to add a print statement to show some part of the code of that we are going to see, let me know in the comments. So I will go back and forth to see the screen of the chat. So that we can do it a little bit more interactive, like as if we were doing a pair programming, and I'm leading. So these are the 3 steps, the 3 parts of the LnMessages library that I want to look at. So LnMessage.commando, the NoiseState.encryptMessage, and LnMessage connect. Maybe first we are going to run some code and see what the LnMessage library offers us to do with the commando plugin. So this is the directory where I am. We are, so bolts, this is the repository of the bolts. Lightning is the repository CLN, and LnMessage is the library because we are going to use it here. We don't need that one. So in the package JSON, so LnMessage is TypeScript JavaScript library. So this is the dependency, and this is in order to use LnMessage locally. So we are going to this gives us the possibility to modify LnMessage as we go, and to use it modified. So here we have this is the script. So you can see on the bottom line. So the bottom line in the mod line. So we have the getinfo.js. This is the name. We have the number of line if it helps you to see a little bit how long a file is and where we are. So the full path of the files. This can be important when we are going to go in the LnMessage repository. This example is exactly the examples that we used in two live session before, but we are going to use it, and I will explain what it does. So at the top, we import net to instantiate a TCP socket, and we import LnMessage as LnMessage.case. We are going to need some information about a node that we are going to run in a moment on the machines, on the network regtest. We're going to see how we do that. And something that we need also is the rune. So the rune is a token that the node can, restriction token that a CLN node can produce to let application use it and run command and on the node. And the command that we're going to run in that case is the command getInfo, but this is an authorization command, restriction command. So in that part, we instantiate the LN. We see that we need the node ID for the remote node public key. So we want to connect to that node, the node IP, and also the node port. And here at that line, we start a TCP socket in order to connect to our node. Then at that line, we connect. So the importance of works commando and the library that send commando messages is really that we this script will act as a node and connect to our node, and this is why we are going to look at both board 8 and board 1 to see the shape of the lightning messages, and also how we can have an encrypted, how can we share a private key between that application and the other node and do the connections. And this is bolt 8. As I'm talking about that, I wanted to do it at the beginning, but I always forget. So this is the moment to thank all the people that use Lightning Network, work on Lightning Network, work on the protocol, because everything that we are going to look at in 1.5 hours, more or less, is a huge work, and thank you for that work. So now, then, once we are connected, we can use that method commando, and what is going to do, it need the method, the param, and the rune, and this is sent to the node. When the node receives the commando message, we are going to see how it looks like a commando message. We recuperate the output, and we print it out, and we exit the process. So there is just a little bug, but I opened an issue yesterday for the version 2.4. LN disconnect no longer works, so we just exit like that. That's it for that script. Now we start our two nodes on regtest. So to do that, in the Lightning repository, we have that script that gives us access to some utilities, to some aliases on the commands that we can use to start a Lightning node on regtest on our machine. So doing that, we're going to start two nodes, and with those nodes, we are going to be able to use them. So if we go back to getInfo.js, what do we need? So we need the node ID, node IP and node port. They are the good one, but we need them too, and a rune. So let's L1 CLI get info, and we want to recuperate the ID. So we have the ID here, and we can see that the address and port of that node are already the ones that are in the getInfo file. So now we can put that here. We need a rune. So the rune, we get a rune for, maybe I should have done that at the beginning, as I use that script often, and in the videos on the live also. Sometimes I forget to tell you what is the L1 CLI. So L1 CLI is an alias for Lightning CLI with the Lightning directory, which is this one temporary /L1-rake-test. So the node is running on there. And with that node, we want a new rune, so that restriction token that we can use to issue command. So take care, the rune that we are using right now, but we are on rake test, so there are no problems, is an unrestricted node. So anyone that or any application that adds that rune can run whatever you want on your node, whatever command there is on your node. So it can run, for instance, withdraw. We have the rune, we have everything, and now we are going to run that, but first we are going to have a new terminal. So this is a new terminal. You can see at the bottom when I switch the terminal, if they are in the same directory, there's a number for to distinguish them. But as we are going to go in LnMessage, right now they're no longer you see that this change at the bottom. So we can see that. What can we do? So maybe we run something, and after we are going to take so npm-install. We are going to install the dependency. There are many because there's also the dev dependency of things. So we don't. It's not the case. So let's see if there are already some question. No question. So we continue. Now we build the library, and you see I am at the commit that correspond to the version 2.4. So now we can see in that directory, so we have the node modules, and we also have the distribution that is going to be used. This is the library that we are going to require. We go to the first terminal, this one, and now. So let's see that. In that directory, we have the get info, we have the package JSON that want to use LnMessage that is locally. So now we can install the unique dependency that is local. And something that is cool to see is that node module and LnMessage. So you see that this is a symlink to the LnMessage that we want. So each time we rebuild the library as the node module LnMessage in that directory is a symlink, we are going to use the new version of LnMessage. So with that said, now let's run, and I hope there is no error. Okay, so maybe to see what happened. So we are. This is what happened. So we run the script, and maybe we can. What did I do? It seems that I removed something. Well, anyway, we have the get info, and this is exactly what we wanted, because we have the console log here. One thing that we are going to do before we switch to the source code of LnMessage is to we can keep this one. We just stop to exit the process, and we are going to see that where is the alias? This one, just I wanted to use it in the other terminal, so I put it there. So I run it here. So in that terminal, that way we are going to we're able to use it. And let's use it, CLI, to see list peer, because this is the really important thing that we have to understand when we use Commando or a library that allow to use Commando, is really that to access to our node, we could have used HTTP from do some HTTP request with some other library. If we run some other plugin, we could use gRPC. But what we do here is really to connect to a peer and send it custom messages that are Commando message. So it's important to see that we connect to something. So let's put the two terminals side by side. So at the bottom, I will run getInfo, and then maybe we can switch them that way. So at the right, I will run getInfo, and then we're going to see. So it's this doesn't quit. So this is this hang, and now we have a peer. So the peer is really the getInfo.js program that is running, and when we send the init message, we said that we have no features. We don't support any features. So basically, we're saying our node, don't send me nothing because I can't do nothings. I will just send you some stuff. So I hope we are okay with that part. So we have a new percent. So this is the getInfo that we have. Remember getInfo. We put again that process. I just drink a bit of water. Okay, so what we could have done to present LnMessage library would have been to say, how does the node connect to each other? Start by looking at that, and then say, okay, so to connect to a node, we need to understand how those Bolt 8 works with the transport layer, which allow to have a cryptographic, how to say, an authenticated and encrypted connection between the node. We start with that. It's a kind of top to bottom or bottom to top. I don't know how to say that, but we can start like that. But I prefer to do it backward, in the sense that maybe let's start by looking at what does LN.commando is doing. So the thing that LN.commando does really is to send a commando message. So what is a commando message? So and we start by looking at Bolt 1 to see how messages are specified, and that way we also we skip the encrypted part at the beginning. We assume it. So let's go now. We go maybe to LnMessage. So this is the library LnMessage terminal. Maybe if this help you, we can look to have not what I wanted. Sorry. So we go in the source, and we are going to do the line of code, so that I like to do that when I look at the project. So there are less than 2,000 line of code, and we have 20 files. Maybe we can look also 3 and less. So we have the entire tree. So we see at the top we have the Shasha library. We are going to This is a library for the encryption. So this is what it used to generate, not to encrypt the message and decrypt the message. We have the crypto file. We have the index.ts. So this is the one we are going to start with. Messages. This is some helper to I don't know if we call that helper, but that treats some different messages. Some of them that are defined in bolt 1 and the command message that is defined in the code of Lightning. The noise state. So the noise state is where everything is the encrypted part of how two nodes can talk to each other, do an handshake, and then end up with a shared private keys, which one with the one they can encrypt the messages. So this part is written in noise state. We have socket wrappers at the end, so it's just a wrapper around the socket. The types and some validation. So this is for the entire library. Let's go into the index.tx. So six lines of code. We import some of the stuff. So there is a little dependencies. The default attempt and what it's this file define the LnMessage and nothing else. So the one, if we want to get info, the one we are using to create the new that new part. So maybe index. So we have the files side by side, and we can see. So we have the remote public key. And then we have the TCP socket. So LnMessage can also work with WebSocket. So if this is a use case that you have, you can use also a TCP socket, the IP on the port. And now let's go back to index. And what we want is the command commando. So let's look for commando, which is defined at that part. So almost at the end of the maybe what we can look at is okay, also side by side. So index.ts at the right and getInfo at the left. And how do we call it? So this is how we call it. So with the method params run and the request ID, I think that is done by itself. So let's see that command. So we are going to unpack. We try to focus on not so much the details of that are from the implementation or from TypeScript, but that are general and that have to do with the bolts. And also this is maybe the moment I can. There is some question now. Okay. I can take that moment also to say that why I wanted to do that live is because Commando is really powerful, but it's powerful only if it exists libraries for different languages. In the sense that let's say that you think that Commando is it's the right fit towards your application, and you want to write your application on a smartphone, you want to use it Flutter, so you write it on Dart. And so there is no library, as far as I know, Commando library for Dart. But maybe you can or we can write it if we have some insights of already existing libraries. Like LnMessage, and I choose LnMessage because it implements everything. But if you look at LnSocket, so LnSocket is another library that works maybe. So this is just stop a little bit what what I was talking about, and maybe we can look at LnSocket just right now. Okay, it's going to be there. So LnSocket do more or less the same thing, and it is written in there's one in Go and also in C. And if we with the C implementation, I think that can target also. Sorry, so Go. So it can target iOS. It can target JS, WASM. And one thing that is cool is that for the C implementation, this library uses the part that implement Bolt 8 and Bolt 1 from Lightning repository. So this is a way to not re-implement or reinvent everything. And for Go, this is the same thing. So if we go LnSocket Go and we look at the top, so they uses Brunted from LND and LN Warrior, and also Tor. So this implement commando, but with only, I think, 2 or 3,000 lines of code, because they reuse this as a Lightning dev kit. Also provide some binding for Java things, for they're written in Rust. So there are many ways to have LnMessage kind of libraries in many languages, but let's continue. So with that stop. So we are in the function commando, and the function, the method commando, at some point will send a commando message which must be encrypted. If we are disconnected, we try to connect, but this is not our case, because in GetInfo we were already connected. So we start with a buffer. So buffer writer is a wrapper on the buffer module of JS, where we can so this is we can write bytes on the buffer, and then those bytes we give them to the encrypted function. This is encrypted, and then we send it. So before we look at all the messages, let's go back. So on the writer, we do some stuff. So we write something here. We go back to that thing after. Huh? So we write something. We write something on the buffer. We write the JSON, which is the commando command with the parameter, and then we are at that point. So we have that buffer, the writer on the method to buffer is just to transform it to the module buffer. So yes, this is it. So yes, why there is a wrapper on the buffer? It's just to adjust the size of the buffer as needed. And then this is sent to the encrypt message. And when this is encrypted, we get that message encrypted, that if we have a socket running, we send that message. Okay, so we send that message, and then there are some of the blah, blah, blah. So we send the message, and we get the response at that point. So we are going to see yes, and we return, and we get the result if we have a success, and we return that result. Okay, so we've seen all of those things. I told you before that we were going to to add some console to print statement to see what what's going on. So first thing is in the writer. So we need a request ID to be sent to just a second. I stop a little bit. Maybe I'm going too fast now. Okay, this is the moment. So at that point, we are writing. If you see those things, so we are writing 3 stuff on the buffer that after we encrypt. So this is the moment to look at bolt 1 and look at how are defined the messages. When we want to send a message in the network, before we encrypt it, there is some things to follow. So we go back to our note, we go to bolt, and we want one messaging. So we have that. Lightning message format. So after decryption, all Lightning messaging are of the following form. So we have first the type, which is a 2-byte big endian field indicating the type of the message, and after we pass the payload, and sometimes we have some extension that are of TLV stream, but I think that today we don't look at those. We just have that. So when the message is decrypted by a node, it will look at the first 2 bytes and say, I understand the type of your message, and I understand your message. I can do something with it. So I know how much I need to read in the payload, the variable length, and how what we can do. There here. So these are for the type of message, and maybe we can look at some fundamental type before we go through. No, it's not this one. The control messages, setup messages. Okay, let's look at the setup messages. So, in the setup messages, for instance, just looking at that, if the type is 16, that means that this is an init message, and in the init message, we need to pass some data on, maybe also, or maybe I not show some TLV data too, which declares the global or local feature. So we have that number. Let's go back to index right now, and we see that the first thing that we write is the message.commando request. So this is the commando plugin that uses 4 types to handle communication with commando request. So we could look at where it is defined in that code, but let's do something. Let's look directly at the buffer we are writing to. So to buffer, this is to get the normal buffer, the built-in type buffer. So now we can use. So if we do toString, this won't work. Yes, if we do toString, it's not what we want. See, yes. So we want to buffer, but we want to read unsigned int, and we want to run 16. So this, that means 2 bytes of the message that we just wrote. So maybe if you've never heard of a big endian or a little endian, this is a way where when we encode a number, where are the important bits, or we use them at put them at the beginning or at the end. So if we want the number 2, and we use 8 bytes on big endian to write that, this will be written so 1, 2, 3, 4, 1, 2, 3, and 4. So this will be how it is written on the buffer. And if this is a little endian, this will be reverse. Okay, so this is just if this was the first time that you see that. Okay, now we're going to look at that message type. To do that, we rebuild the library, and I hope I didn't make mistake. And now we can go back at that point. Maybe we can just change a little bit get info, because we don't want to see all those get info. We assume that this is working and do the commando request, but we don't print that things, and we just want to see the type of the message. So maybe do you have some question about what we are doing? This is where we take a little break to drink. I hope I'm not confusing you. I didn't find a better way to go through the code and look at how it works, because there are many aspects and many things to look at. So I try my best to make it clear. Okay, so no question. So we have this is the type. So when we send the request, commando will look for will read this custom message with the first 2 bytes and say, okay, this is that type, and as this is that type, I know what to do with it. So maybe we can go to, yes, because the fun things today is to read code. So let's go to Lightning commando. So we are not going to look at everything, but we can look at those message type. So at the beginning, we have the commando message type, and we can see. So we are going to use that calculator, and we can do something like that. So I'm a little bit cheating in some way, because I know what to look for, but it's just that, okay, so as this is written in hexa, so this is how it works, the calc, so 16 hash with the hexa that we have, and we have it printed in decimal. So this is what we are. This is when we write a commando things. We are sending that. Why there are four types. So this one is because when there are some commands that might have a lot of data, and that can exceed the size, the authorized size of the messages. So that way, first we will receive, for instance, the if we are the when we that way when we received the thing. So first time we might receive that type which say, okay, I reply to you, but there are more to come. So we read more up to the point where the message starts with command message reply term with that type. So it uses for to do that. As we are talking about the size of the message, cool. So this is an opportunity to go to commando. So let's go back to the note, and we are going to look at bolt 8 transport. So this is where is the specification on how to the two nodes can share a private key. We're going to look after, and as this uses the noise protocol framework. So this one. So this is the references in bolt 8, so that can be found there. We have the limit size, so where it is, so 35. Okay, so the maximum size of any Lightning message must not exceed that number of bytes. So we can read further. It says that it simplifies testing, make memory management easier, and mitigate memory execution attacks. And it seems at first when I read that, it seems that not random, but why that number? And we can see there that this is something that this is not a choice from Lightning. From the Lightning protocol, but maybe 65. Okay, so we have it here. So this is something that enforced by the protocol framework used by the Lightning network. So with that said, if we go back to commando, this is why we have a type that is that might continue. We go back to messaging. We remember. So what was the one? So this was this one. So Lightning messages. So rewrite the type with the two byte, and then the payload. Let's look at the payload of the commando messages. So we were there. So we write the type. We need to pass an ID. It happened that this ID must be of 8 bytes, and this one on the hexa. Then we have that. Then what we want is to write those bytes to the buffer, and we can see this is how does it look like a commando request. So there's an ID that make it unique. We have the rune. So the rune is important. Is really the restriction token that say if we can use the method that we pass here, and that method in our case, so if we go to get info, our get info takes no parameters, so we don't pass parameter, but it could have been an invoice or a pay command, and in that case we would have needed to pass those things. Maybe let's print that writer. Maybe we can print writer to buffer and to string. Yes, let's try this one. To buffer and to string. So now this is the message unencrypted that we want to send. So let's rebuild. So terminal. We go back to that terminal where we build the stuff, and in another terminal, this one, we are going to run get info, and this is what we get. So we can see that this has the first 2 bytes. This is the unique ID, and after this is a normal JSON. No, it's not a JSON JSON RPC request, but this is something that Commando will understand with the run, the method getInfo, and the parameter. So now let's go back here, and maybe I think that is message. I think that message is also a buffer. So let's okay. So I think this is a buffer. So now I don't know. See if it's 2 buffer. Okay, so let's see encrypt message. I want to print those 2 messages together, but we need encrypt message in the noise state. Encrypt message. So yes, it returns a buffer. So let's try that. So as it shipped to try, let's try. So what we want to do now, it's really so. So read-only array 2 buffer. Okay. Yes. So this is because this is not. This is a built-in buffer. This is not a write nor a read buffer from the library. I think this is the error I've just done. So let's look at that. Okay. The terminal, and now what we want to see is the type and the 2 messages. One which is not encrypted, and the other that is encrypted. So it's a super. So this is that one that we have encrypted. Yes. So here we are at that step of this. So we've looked a little bit at those things. So a message as a type, it can have, it will have a payload also, and after it can have more data that are encoded on the TLV. So type length value. So if you want to read more, you can read more, but it's not what we are going to do now. And that message is encrypted thanks to what have been done before that, to connect and have an encryption a shared key from the 2 nodes, from getInfo.js that is not a node but act as a node, and the node L1. So before we go further, and we have 37 minutes left, do you have some question about the messages, about Bolt 1, about LnMessage, LnSocket? Is there something that you really want to see? So let's see. Hey, so we have Mike Satimoto. Hi, guys. Okay, so let's continue. So now, because the last part is really interesting too, so we are going to look at, I will speed up a little bit to cover how the noise, at least how we can understand why the noise protocol framework works. So let's go back now to our index. Maybe we're going to comment those one because we no longer want to see them. And we were to see, okay, encrypt message. So once it's encrypted, the socket.send, it's just that it's a wrapper that writes on the socket. So we don't have to look too much at this. But what's interesting is the noise state. So why it is called the noise state? It's because so let's look at, because it's well it's more if we just read okay, so what is the purpose of yes, this is that part that that is really that explain everything. So the noise protocol begins with two parties exchanging and check messages. So in the case of the Lightning Network, there are two free end check. So the initiator, in our case, which is getinfo.js, that will send something. Then our node will send us back something else, and at the end we share the getinfo.js share on the encrypted way is a public static key, so the node ID key that getinfo.js adds, and at the end, so at the end of the incheck messages, so there is this incheck. The party exchanges DH, so diffie-Hellman public keys, and perform a sequence of diffie-Hellman operation, hashing the diffie-Hellman result into a shared secret. So the important part is at the end, they end up with a shared private shared secret, shared private key that they use to encrypt and decrypt the messages. Okay, so after the handshake phase, each party can use the shared key to transport the messages. Right now, when we are at that point, exactly, so let's go to transport, to the bolt 8. And what is... But there are two things that I want to show you right now. So, okay, so when there is an handshake, there are 3 steps, and we are going to look only at the last handshake. So this is a notation to say, so from the initiator to the responder, getinfo.js is the initiator, and it sends is private. No, it's sorry. So yes, so it sends its a static public key, and also sorry, I missed up the SE here, but anyway, we can continue. So there are a lot of stuff that are happening here, but input, everything is important, but okay. So at the step 6, at the end, they created SK and RK using hashKDF. So for hashed, key differentiation function, and sorry, so I don't want to mess up. It's okay. Okay, so at that point, for the two, for both, they have CK, so the chaining key that is the same. They will use a zero length plain text, and from that, with hkdf function, they generate two keys, two private keys, which are going to be the same. One SK, which is for sending messages, and RK is for receiving messages. So it helps to see that here, because this is used at that point. This is used 2 times. So here, this.sk, this is for encrypted the message with that key, and they uses a nonce. So this is a number used only once, and this one is incremented. Sorry. Okay, it's clear for me, but I'm not sure if I'm doing the job in the good way. So let me go back to the index, because we are here and we used NoiseState.encryptMessage of the buffer. So this one is the buffer, the M that we have here. Now, what we want to do is to encrypt that message. To do this, we are going to use that key, which key, private key, that is the same that the node has, because after all the uncheck systems that they've done beforehand. They uses a function here, CCP encrypt, which is for Shasha poly, the Shasha 20 poly 1305. So this is the encryption that has been chosen to do this, and they encrypt. There are two moments where things are encrypted. Okay, there are those 2 lines, and then we do something else. So now we have to go back to the transport, to board 8, and see the lightning message specification. Okay, so how do remember that we have our message not encrypted, and now we want to encrypt it and send it to the other node. To do that, we use Shasha poly. So let's just say that we use that, and if you want to read more, you can read for that, and that we encrypt, and also so we have the length of the message that we want. So let's go back to get info, not this one, to index. Here we have the message unencrypted, and with that message unencrypted, what we board 8. Okay, so what we do is first we get the length of that message, and we encrypt the length, because we don't want anybody in the looking at our communication to see the length of the message. So we encrypt that message, and we also generate a 16-byte MAC, which is a tag that allow, if I understood correctly, that makes that if someone try to tamper the length of the message, the MAC won't be the right MAC, so we can see that. So we do that. So this is 18 bytes, and we continue here. And what we do is that we encrypt the message with the same function Shashapoly, and we also generate 16 byte MAC of that. We concatenate all of that, and this is what we send to the warrior. Now, this allows us to understand better what we are doing here. So we have the M, which is the message unencrypted. What we do after is that we write the length of the message, and we encrypt that length, and this return also the length with the MAC. There's something that need to be done, that in the encryption we are using a nonce, but what and the nonce, the sending nonce is incremented each time we do an encryption, and when we are at 1000, more than that, what we want is to rotate the key. So the S key that we have to that we want to send, when we've used it 1000 times, which correspond to 500 messages with the Shashapoly encrypt, we need to recompute a key to encrypt the next messages. So we have to do that after each time we to check that after each time we encrypt something. Then we encrypt the message, which do the same, and we can see at the end that we return the concatenation of so let's put that side by side. Maybe it's a little bit more clear like that. So we have those two. So LC, this is the length encrypted with the MAC. So these are the first 18 bytes, and then we have the other. Okay. So we've done that, and I hope you're still with me, and it's not, I didn't mess with you. So any question? Okay, no more question. Let's continue. It's maybe it's I don't know. It's a topic that a little bit confusing to try to explain. But anyway, we are here, and we have the encrypting phase. And do we want to print something or nothing? Okay, so maybe we can just print M as the buffer M when it comes, just to see something. Is that when we have finished that unchecked part, that is to find a way to share keys, private keys together, we have to send the first message, which is init message of type 16. So maybe we can do something like that to see that that function is called 2 times when we run getInfo. So m, and we want maybe toString. Let's build again. And normally we should see 2. Okay. Why we don't see 2 messages? I don't understand why. So let me just, I wanted to, because if we encrypt message, it should be used twice. How to see the... Okay, so let's just check that to see if maybe I'm missing something, and this is not it's not a problem, but okay. So foo has been printed. Okay, so foo has been printed twice. Okay, so it seems that this something is happening. So maybe instead of toString, we might try something. So read. Okay, yes, maybe we have something interesting to try. So let's read the message unencrypted. And we read the first 2 bytes, and we should see we still keep the foo because I like to see it. Read an insight in, so we should see something. So I hope that we are going to see something the 16, and that we are going to see foo 16 and foo. I don't remember 19,000 or something like that. Okay, cool. So I was thinking that I was no longer understanding anything. So yes, so in the noise state, so the encrypt message, we see that this has been called twice because when we so message this one, I think that in bolt 1, this is they tell us that. So I don't remember where I read it, but I think it's in bolt 1. So when once we've done, how to say, the uncheck, we are at the point where we have both the private keys, so we can use them to communicate. But first, we have to send the private the init message where we show our features. So the features that we support. And we've seen before that getInfo.js support nothings. So okay, so I have 15 minutes left. Maybe I will use 5 of them to go a little bit no longer on that no longer in the code of LnMessage, but just read with you a little bit bolt 8. and gives you one thing that helped me understand why at the end the keys are the private keys are the same. So this is the only thing that I can try to share with you that is important. Any cryptographer would have seen that from the beginning, because it's seen that many of the things that are used are standards. And I hope with what we've done, you might want to read those two boards, maybe read a little bit of LnMessage, and see that there are some of the things that can be understood with some printed messages. But let's go to the transport, and we've seen how the messages. Okay, to summarize what we've seen, so we've seen that when we send a message, when it is unencrypted, it should have the type, the payload, and maybe some additional data. All of this, when we have the shared private keys, we send the message encrypted with the length encrypted with Shasha-Poly, and also the MAC tag of 16 bytes just after, and we do the same with the encrypted with the message after. Let's see the key rotation. So at some point we've seen that we have S key and R key, which are the keys that we can use alongside with Shasha-Poly encryption to encrypt and decrypt the messages. We also have a chaining key that have been computed in some way, and we have some nonsense. And when we've done more than 500 messages, we have to recompute the key, and this is done always in the three phases of the uncheck and this protocol. This uses HKDF, which is for key derivation function. And here we uses the chaining key and RK or SK or what is the one, or this one, and we have to change the nonces to reset the nonces also. So this is something to have to taking into account. And now let's see the uncheck. So it would be great if I show you the name of the. Okay, so we have some of the things that can be done. So in the Act 1, we will send 50 bytes in the from the initiator. So the initiator is getInfo JS. The responder is the node L1 in our case. So the initiator send some information. Then the other send other information, and at the end, this is a 66 byte. This is at the moment where the initiator getInfo.js send is node ID. So throughout the process, so we have we have some information that are used, the chaining key, hash, the uncheck. So maybe I will go through this and look at the function. So to me, we have this one, HKDF, which is for a key derivation. So once we have calculated with the previous function etcdh at some point in the protocol, we generate key with HKDF, and we pass some information here, and one of them is something that we get from the ECD hash, if I remember correctly. And the ECD hash, so this is an information. So let's go back to the node. So we are almost done. I want just a link. There are some things that make it Diffie-Hellman key exchange. Are we going to see it? No, I can't see it there. So I let you see this graphics if you've never seen this one. So the thing that makes everything works is really that with the public key of the other node on my private key and the other way around, we can generate. It's not really a DOS key, but if two people, Bob and Alice, want to do something, they can generate a private key that nobody can get just using their private key and their public key. So to me, it was something that makes everything work. So let's write it like that. So if we have Alice private key and Bob public key, so this will this is equal to Bob private and Alice public. So this one line that seems okay. So this is for me the thing that when we look at this, we get that thing, because when we start the uncheck, so we start both nodes will start with a hash h, this one with which is the SHA-266 of the protocol name, which is not noise xk sec. So all of those things, they start with the same chaining key, and the same the hash is recomputed here. So with those things, after in every act, they generate. So what we see, so there's 2 more minutes. So at each point, there are an ephemeral public and private key that is used, and the public key of the ephemeral is sent. Here we see that we do an ECDH with the ephemeral private key and the remote static key. So this is the remote public static key of the node, and then we derive some key here that we use to encrypt stuff. Okay, and I won't go more, because I think I'm messing around, and maybe it's not that helpful that I go there. I tried my best to do that live and try to go into the transport layer, but I think that maybe I have to work a little bit more and to understand those things. But anyway, if you want to go further, remember that that part, okay, we want to, with public and private key with Alice and Bob are equal, and at some point when we do the derivation and we go back, we go at more. So it's almost the same. So we exchange ephemeral keys, we use the right nonces, and we get to the end. So this is the last act, where we calculate, you see the three, so I will put them. We are at the Act 3, so this is the last thing that we are going to look at. Okay, so Act 3, so the sender action at the left and the receiver action at the right. You can see that this is almost always the same. But the important part is that one. Look, so part 3 of the sender action, so the initiator, is calculating an ACD hash with stats is a node private key and RE, which is a remote public key of the node. So what they obtain is SE, which is used after at that point with HKDF, and the CK is calculated in such a way that this is the same for the both. And now we go at the right, and you can see at some point we calculate an ECDH so that we've seen before, and this time we use it E, which is the ephemeral key that corresponds to the private part that has been calculated in the Act 2, that and that the public part has been sent and calculated that we've seen just before on the left. And we use the remote static key of the node, the initiator, which is getinfo GS, to calculate SE. So at that point, we have the same ACE, we have the same CK, and so when we go down and we go to the step 9, and we derive key derivation functions where we derive the key, we obtain in both cases, so 9 on the right and 6 on the left, we obtain the same private key that can be used to exchange the messages. Okay, so this is all I had for today. And maybe if you have some questions, some comments, or maybe just say me, yes, you don't mess up too much. But really, it's super interesting. And if you have some time and you want to dig into Bolt 8 or Bolt 1, we take them for granted. And just that, yes, Lightning Network is peer-to-peer, and it's secure, and we send stuff encrypted, blah, blah, blah. But really, there a huge amount of work that have been done by many people. So thank to them, and really, this is impressive. I also love Commando, and thank you for all being there to that session. And that's it.
Thank you, Tony. This was fun.
Thank you, Drew. See you next time.
All right. Have a good one, everyone.